Welcome back to the Rat Lab. I would like to provide a quick update on my project to build my own Z80-based computer. In my previous video, this project started with learning to mill my own PCBs and resulted in a 10-pin proof-of-concept bus. After considerable trial and error, I have progressed to a full 64-pin bus. I will provide updates as to what I've changed in my milling process. I will also demonstrate some of the electrical characteristics of my bus as I prepare to ultimately work on handcrafting my second generation computer, the Z80 MP80 Mark II, the first generation which still exists as a breadboard prototype. So please, join me. The first update to my process was replacing the Genmitsu brand MDF spoil board with HDPE, or high-density polyethylene. I did this for two reasons. First, the drilled holes in the MDF board caused little tiny volcanoes that prevented perfect flatness. Also, the MDF fiber board absorbed the cutting oil that I use for lubricant, which ultimately affected the adhesion of the double-sided tape and likely was or would lead to swelling. The second update was that I switched from a 60 to a 45-degree V-bit in order to try and get more consistent traces. One lesson learned was that with the HDPE board, my double-sided tape had significantly higher adhesion, and I had to find a putty knife in my toolbox to eventually separate the PCB from the table when I completed the milling. With these changes, I was ready to take the next step for my proof-of-concept 10-pin bus and attempt to mill my full design, a 64-pin bus with 5 edge connectors. I did 2 versions of the backplane. The first version I did before the table upgrade suffered from variances in the resulting copper traces. Also, there was some design inconsistency that led to a couple of pads not being properly isolated. This required separating them with a blade and bodging the connection. Although there is variance in the resistance measurements on the traces, and it is not pretty, electrically it works well enough for my testing. The second version of the bus uses narrower square pads, which allows for thicker traces, although at a cost of pairs of traces being closer together. Between the two buses, I am able to successfully test my circuits. You can see the result of the increased trace width on PCB 2. For PCB 1, most traces had a resistance of 1.5 ohms. This measurement varied as there was variance in the result of milling due to PCB imperfections. For PCB number 2, all traces measured a more uniform 0.5 ohm of resistance. The goal for my current project is to build up a minimal Z80 computer using multiple function cards and plug them into my bus so that they may communicate together. For the function cards, I will use perf board prototype PCBs and will hand wire most of the circuits. In my last video, I noticed ringing on the clock signal when testing my mini bus. So for my first test of the full bus, I am connecting a clock circuit to the full bus and will be looking at the signal both on the near and far side of the transmission line. The blue signal trace is connected directly to clock output. On the right side of the screen, you can see that the peak-to-peak measurement is 5.2 volts, or very close to the 0 to 5 volt expected. Now we overlay the yellow signal, which we are measuring connected to the unterminated bus, otherwise known as a transmission line. Notice both the ringing and the peak-to-peak measurement of 6.3 volts, approximately 1 additional volt. although our circuit will likely work just fine, we do want to try and reduce the ringing and get our peak-to-peak closer to the nominal 5-volt range. To do this, we are going to add series termination, which is just a resistor added in series between the source and the transmission line. Since I don't have the capability to calculate impedance of the transmission line, I am simply going to use a trimmer potentiometer in line, adjust until the trace looks acceptable, and measure the resistance to help choose an acceptable resistor. The goal here is to get close to 5-volt peak-to-peak and minimize the ringing, not to overcompensate by shooting for a high resistance value. We start with a resistance value near 0 and adjust upwards until we are happy. Now we will measure the value of the trim pot. Based on this measurement, we will locate a resistor in our junk bin with a value approximately 40 to 60 ohm and call it good. So why not shoot for a perfect match? Because a lot will change electrically before this project is done, and I will revisit circuits and values many times before the design is set. Now I will test the clock signal on the perf board circuit, which includes the series termination resistor. I am now using the breadboard only as a power source and will plug the clock card into slot number 2. And the oscilloscope probe remains connected to slot number 5. And I believe the results are acceptable. Thank you for watching, and I hope that you will come back for future videos as I continue my amateur journey in electronics.